I'm David Christiansen. I work at a little company from originally Portland, Oregon, that we've spread a little bit, called Galois. Portland is where the weather is best. I'll stand by that forever, except maybe Copenhagen. So bidirectional type checking is a technique for implementing type systems. And when you want to implement a type checker, you've got to sit down and answer two questions when you're sort of making your initial plan. The first of those questions is, which types in my type system are compatible with each other? In some type systems, this is a very easy question. Like, if the only type you have is int, then all of the types are compatible with all the other types. Let's say you have int and bool. Well, int is probably compatible with int and bool with bool, and maybe int and bool are also compatible depending on what kind of a language you're making. But as your type system becomes more interesting, this question becomes harder to answer. For example, if you have function types, then you may need to do a recursive traversal of the tree structure that represents the type to figure out if it's compatible. And as your type systems get more and more interesting, you start having to do things like instantiate type variables with concrete known types. For example, if you're implementing a language like ML or Haskell. Or you may need to run the programs embedded in your types and then check the results for alpha equivalence if you're implementing a dependent type system. This is a very important question, and it's not one that I'm going to talk about today. Instead, I'm going to talk about the other question that you need to answer, which is, when should we check whether two types are compatible? And really, you can see bidirectional type checking as one way of answering this question that has a lot of nice properties. It's far from the only way, but it's one that tends to work pretty nice for a lot of things. So I think it's a good technique to have in your bag. So in particular, why do we want it? Well, first off, it scales to complicated features much more readily than many other strategies. In other words, you can use a bidirectional type checker to implement a dependent type system. You can use it to implement sort of polymorphism of arbitrary rank. You can use it to implement systems with subtyping. And before you start poo-pooing all those object-oriented people, realize that if you're writing a dependent type system with cumulative hierarchy of universes, then you're going to need subtyping. Another nice feature is that you typically only have type annotations at the top level of your programs, which is to say, like, when I sit down to write a Haskell program, I will sort of write down the type, and then I'll write down the program, and it mostly works. And when I'm using a bidirectional language, it feels the same way. Like, I have to write down the type often, but I want to do that anyway. I don't have to write lots of other types sort of peppered throughout the code, which is quite nice. When I say usually only at the top level, that's because there's an exception to this, which is that an explicit regex will often also require type annotations. So if I am the kind of person who would rather write lambda x plus 4 applied to 2 instead of 7 in my code, then I'll have to put in a type annotation for that lambda as well. This is something that I think most people can live with. And the other really nice thing is that error reports have a clear and predictable source location. There's no guarantee that it's going to be the one most readily understood by a user, because that's a complicated problem of human psychology. But at the very least, it's a predictable process, so users can adapt themselves to their tools if their tools have not been good enough at adapting to them. So before I get started, I want to fill you in on some background things. We rely very heavily on the concept of a judgment when we're talking about a type system. And I like the way that Frank Fenning describes it in some lecture notes. So a judgment is something that we may know, that is, an object of knowledge. And then when we come to know it, then we say that the judgment is evident. And if you want to take a picture of the screen and go read those lecture notes, they're really wonderful, so I highly recommend it. So one of the judgments that we see is the one that on this slide looks a little bit like a polar bear sideways in a blizzard. But in fact, it is not that. It is in fact a piece of punctuation, which is a colon. And the colon separates an expression from a type. And the meaning of this, when I read it, is that the expression E has type T. And many, many type systems have this particular kind of a judgment. When I say form of judgment, what I mean is like a judgment with holes in it, which is to say, like, E here doesn't mean like I actually wrote an E. It's a variable standing for some arbitrary expression. And T there is not like the single type called T. It's a meta variable standing for some arbitrary type. And so this is a form of judgment. And in most programming languages that I care about, There's also a little thing called a variable, and if we want to know what types the variables in our expressions have, then we need one other piece of information, which is called a context. And the context is conventionally represented with a gamma. That's just a letter, and it's standing for a sequence of variable type pairs, saying like this variable has this type. And then it's separated from the context in which from the area in which those variables make sense by this symbol here, which is the turnstile, named after these things. And when we want to talk about the conditions under which we know something, in other words, the conditions under which a particular judgment is evident, we use a notation called inference rules. And so an inference rule is a horizontal line with a judgment under it. That judgment is called the conclusion. And if all you have is a horizontal line with a judgment under, then the conclusion is said to be self-evident. In other words, we don't need to know anything else, we just know it. On the other hand, you can also have other judgments above the line. These are called premises, so I'm writing P for premise. And the meaning of this inference rule is that if we know P1, then we know C. And we can have more than one premise, so we can say if we know P1 and we know P2, then we know C. And if we know P1 and we know P2 and we know P3, then we know C. I could keep going, but I'm not gonna. And now I'm going to walk you through how you might use some inference rules. I'm not gonna write down what the actual rules are yet because I think it's instructive to use the thing before seeing the definition of the thing sometimes, and I've just been defining things all day. So I'm going to show you how to know that lambda f, lambda g, lambda x, g applied to f of x, is a function from a to b to b to c to a to c. And here a, b, and c could be any old types. Well, the first thing I need to do is go down into the body of the function and check that out. But when I enter the body of the function, I remember what type f had to have. So in other words, f we know was a function from a to b, if this whole thing's gonna ever work out. And now we have the task of determining that lambda g, lambda x, g of x is a function from b to c to a to c. Well, we go under the lambda once again and kick the g over to the other side of the turnstile. I hear that hopping over turnstiles is a thing people do here a lot. I think g needs to get a ticket. So we have in our context where f is a function from a to b and g is a function from b to c, that lambda x, g of x is a function from a to c. Well, that miscreant x is going to hop the turnstile once again. So we have now a new task, which is not a lambda. We need to show that g of x is a c. And in order to know that, well, it's a function application. So there's a function, and there's an argument. And, well, the function had better be a function, and the argument had better make sense. So to ascertain that g is a function, then we're going to see, well, it's going to be a b to c. And so, well, if we look in the context, we see that g, in fact, is a function from b to c. So we're done. Yay! But we're not quite done, because we haven't checked the argument yet. This derivation, a derivation is the name for this tree put together out of inference rules. It's getting a bit wide for the slide, so I'm going to abbreviate that context right there, and then introduce the other premise that we need to show for that function application to be right, which is that f of x is a b. Well, we've seen how to deal with application. So we first check that f is an appropriate function, which indeed it is by looking it up in the context. And then we check that x is a suitable argument to that function, which is to say an a, which we can also find from the context. So it's done. We've shown that function composition has the right type, and now we know it. So some of these inference rules that I've been using, the first one says that if we want to know that x has type t in some context gamma, then we look up x in gamma and see indeed that it is t. Likewise, for lambda, if we want to know that lambda xb is a function from t1 to t2, then we extend gamma with the knowledge that x has type t1, and then check that b has type t2. And the other rule we used was application, where if we have E1 applied to E2, and that should be a T2, we first have to ascertain that E1 is a function, and gamma doesn't get touched. And we also have to check that E2 is a suitable argument to that function. And if I want to write this down as a program, the first thing I do is I go and I write down a data type that stands for my types and my expressions and all the other things that I care about. I've already done that. It's on a secret slide that you don't get to see. You may notice that this programming language doesn't look like a programming language that you're used to. So that's because I thought, well, I want people to be able to understand this talk if they don't know what monads are, but I need to be able to throw exceptions, so I can't use Haskell. I also like using 1 colon for the type separator. And on the other hand, I really want to have multiple equations for the pattern matching, so I can't use ML, so I had to make my own. I hope you can follow along, and please interrupt if there's a matter of like interpreting what the code examples are intended to mean. So in order to find the type in gamma of some variable x, well, I can replace my whole with a match. So I look up x in gamma, and if I got back some t, then that's the type, so I can just return it. And if it wasn't there, then I raise type error. In a real implementation, type error would be a much more informative collection of exceptions. They would include the source location of the term that I'm currently type checking. They would include a lot of information, like not type error, but instead something like X wasn't found, I'm on line whatever. But you know, the constraints of making a slide is a harsh prioritizer. And if we have function application, well, to find the type in gamma of fun applied to arg, I find the type of fun, determine that this type is indeed a function type, because if it's something like int, then I'm just going to give up and throw a type error. And if it's a function type, then I check whether the type of the argument is the same as the type of arguments expected by the function. And if those are all okay, then I return the function's return type. Otherwise, it's a type error. And if I have a lambda that I want to check in gamma, or that I want to find the type of in gamma, well, I extend the context with something. What do I extend the context with? So if we think about the rule, it said that we need the type of arguments to the function, but we don't have a type of arguments to the function. And in some type systems, like in Kenny's talk yesterday, we can use unification to say, hey, tell me later. But we don't necessarily have unification in any type system we want to make. So instead, I'm going to back out, and I'm going to do something different. So the first thing is that, well, if we look at our type x in T, and that was fine, but we had our real problem, right, when we came to this lambda rule. So I'm going to take lambda, and I'm going to stick on some more information. I'm going to say, anyone who ever uses my programming language had better tell me what type the variable is that the function is binding, and then I'll use that information in my type checker eventually. And then function application was also okay, so we can leave that alone. So I'm going to represent this just for emphasis to say that the version in which we expect to be able to check or to determine the type exclusively by looking at the context and the expression, I'm going to say we're synthesizing a type and represent that with a right arrow instead of a colon. So now that we have more annotations, the variable rule remains the same. We look it up in the context. The application rule, that remains the same because there's no more work to do than before. But lambda, we can now extend the context with the type that the user specified, T1. And then we can find the type of the body, and when we're done, we return the type arrow T1, T2, because it's a function from T1s to T2s. Success! Or is it? Mandatory type annotations, first off, can be kind of unpleasant. I know I like to write the types down first and then write the program down rather than interleaving these two processes, because I see a type as my expression of my intention to the computer as to what I'm going to do so that it can help me do it. And if I have to interleave these two activities, then I don't get the same kinds of assistance. Also, I have to look all over the code to see where the types are rather than having them in one place. So it can be unpleasant. But maybe you're not like me. Maybe you like interleaving them. So that's not a convincing argument. Even worse is that we also need annotations on many other constructors. So for example, the empty list does not have enough information to tell us the type of entries in that list. So in order to be able to synthesize a type for the empty list, we actually have to like stick a little notice there saying, hey, it's going to be a T. And that's starting to look unpleasant. And then it kind of doesn't scale to all the type systems we care about, because it's really going to require that every expression is going to have like a unique best type, because we don't have any way to like make decisions about other types. And that's a problem for more interesting type systems. It works great for inexpressive type systems that can't say very much, like ML, Haskell, these kind of things, but there's more in the world than them. So let's try again. So it doesn't work to look at the expressions and always say, we're going to get the type out. Maybe it does in certain like restricted cases, but in general, it's not going to. So let's try again. Instead of having the type be something that we have to discover from the lambda, we're going to say that you tell me what the type is, and I will check that the thing you gave me has that type. So in other words, the types are coming in from the outside toward the program, so I'm going to represent this type checking with a leftward-facing double arrow instead of a colon. So lambda x.b can be checked to have the type t1 arrow t2 when we can check that b is a t2 under the assumption that under all the assumptions we had before and the additional assumption that x is a t1. And when we're doing function application, well, we're going to check that e1 applied to e2 is a t2, and so then we need to check that e1 is, oh wait, where's t1 coming from? Let's do that in code to make it very clear where it goes wrong. So if I want to do type checking, so for variables, I'm still in good shape. I call this helper function variable type is, and that does the lookup, and if it's found, then it just checks the type that we found is the one we expected, and throws an exception otherwise. For lambda, we're still in good shape. So because we have an expected type, we can analyze that type to find the type of the argument, to put into the gamma, and check the body. So far, so good. But when it comes time to check the type of the function in a function application, then we're stuck. Because we know it needs to be a function, but we don't know what type its argument needs to have. So what are we going to do? We have some things that work well with checking and some things that work well with synthesis. Yeah. And actually notice that the way I wrote that system down, you're in really big trouble, because you can't even know that if fib is a nat-to-nat function, that fib3 is a nat, because how are we going to discover that the function is, how are we going to check that? Uh-oh, like what are we going to use to check, right? Because in order to recur down the function position to get to where it could check that fib is a nat-to-nat, it would need to know that it was supposed to be nat-to-nat ahead of time, rather than discovering it by looking up the variable fib. So this is like even worse, right? So even harder is when we have subtyping. So for the rest of this talk, I'm going to be showing you an implementation of a type checker for a language with subtyping, simply because it presents a lot of nice, unique challenges, and it's a place where bidirectional type checking can really shine, and you can see how it works. So this form of judgment here is read T1 is a subtype of T2. And so the meaning of this is that wherever I want a T2, I could just well have used a T1. It doesn't necessarily go the other way. So my favorite example is that the natural numbers are all integers, but there are many integers that are not natural numbers, such as -1 or -2 or -11 billion. So to formalize this just a little bit, it is self-evident that nat is a subtype of nat. It is furthermore self-evident that nat is a subtype of int, and also that int is a subtype of int, because wherever you need an int, you can use an int. Lists are what we call covariant. So what that means is that, as an example, if you need a list of ints, you can just as well provide a list of nats, and it'll be okay. Functions are a little bit tricky, because if you look at T1 and T3, they're flipped around on top of the line. In other words, the way to read this rule really is to say that a function type is a subtype of another one if it is at least as liberal in what it accepts and at least as conservative in what it produces. Then you can use it in place of the other. And the way we use this subtyping judgment together with our typing judgment is with a rule called subsumption. And so what subsumption says is that we can know that E is a T2 if we know that E is a T1, and we know that we can use T1s where we can use T2s. So this rule here is a real pain. And the real problem is, like, how do we know when to use it? So all of our previous rules, if you looked at the conclusion, there was something that would guide you to, in your implementation, to say, hey, now I need that rule. Like, you could look at the expression and say, oh, the expression's a lambda. I need the rule with lambda in the conclusion. Oh, the conclusion is, I've got a variable, so I need the rule with variables in the conclusion. But this rule, this just has an expression and a type. So now, at every point in time, if we're going to use the previous implementation strategy, we need to sit down and say, like, oh, well, am I going to do a subsumption check? And if so, like, what type is T1 going to be? And it's very, very confusing. So we have this problem, which is that the type system isn't syntax directed. And so syntax directed means that the choice of the rule that you're going to apply only depends on the expression or the type that you're checking. In other words, you can examine the problem that you have, and there'll be a rule where you look at the conclusion and you say, that's the one I want. In particular, you're not guessing anything. Like, you're not having to sort of enumerate all of the types and try them out, which is sort of, I guess, the prologue implementation of type checker's approach. And also, you're not backtracking. Like, it's not like, oh, well, I tried subsumption a few times and it didn't work, so now I'm going to try this other rule. A syntax-directed system is one where you can really read it directly as an algorithm, which is quite nice. And so the bidirectional type checking solution to these problems that we've been seeing is to first split the typing judgment into both checking and synthesis modes. So we've seen that checking alone is not sufficient. We've seen that synthesis alone is not sufficient. And, well, together, maybe they're going to work well. It's like Captain Planet, your powers combined. And all the 90s kids are laughing. And so the next step is that we need a type annotation syntax. So if your language doesn't have a way to sort of document to the compiler, this expression down here, it's got this type, you've got to add it. Most languages have it anyway, so this isn't too onerous of a restriction, but it is a thing you're going to need. Then you add some rules to your system that talk about how to change directions between checking and synthesis. And then finally, the hard part is when you have to sit down and choose what direction to use for every piece of syntax in your language. So the bidirectional forms of judgment that we have are the synthesis and checking judgments. So gamma turnstile E right arrow T, that's to be read, expression E synthesizes type T, and E left arrow T is expression E can be checked to have type T. And when we think about this algorithmically, we really have two modes that we use for the different positions in the forms of judgment, which are inputs and outputs. So in a type checking problem, we have 3 inputs. We have our context, we have our expression, and we have our type. And in a type synthesis problem, we have 2 inputs and 1 output. In other words, it's going to either return the type or throw an exception. And I'm sorry, on the second row there, the T at the end of the line should be blue, in case you're confused, because it's an input. And so if we translate these meanings into type declarations for our implementation language, then synthesis is something which takes a context and an expression and gives us back a type. It may also throw an expression, so this type is an exception, so this type is slightly a lie. And there's also type checking, which gets a context, an expression, and an expected type, and then will, I mean, it's going to return unit, it says, but it may throw an exception as well. And our syntax for type annotations, well, I've already got colon used in my implementation language and in my judgment languages. And having another thing called colon, I think, is a problem, so I'm not going to do that. And double colon is morally required to be the list constructor, so I'm not going to use that. And so I've got this, I decided to use this sort of element of notation to say E has type T. This is not a judgment here, this is just an expression. So we've added another kind of expression. So how do these expressions work to change directions? So the first case is that if we have a type annotation, in other words, the user has told us that E has type T, then, well, we're going to be able to synthesize the type T for it because we can just look at the expression and see the type. But as Kenny quoted Ronald Reagan quoting a Russian proverb yesterday saying, "Trust but verify," we check that E in fact has type T before we just return it. So that way I can't say, like, write down a string and say it's an int and the thing is like, yep, okay. And in type systems that are more interesting than the one I'm implementing here, I also need another judgment which says T is in fact a type, and I need to check that here. In this language, like, being representable by the data type of types is enough, so I don't have to do it. But keep that in mind when you start implementing things like dependent types or types with variables in them and those kinds of things. And the subsumption rule is really replaced with the other direction change rule. So we have an E and we have a T coming in, and, well, looking at the bottom, it looks just like the subsumption rule. So why does this get to count as a thing we can use in an algorithm? And it gets to count because it's the only one. So this is the final case of our type checker. And if we've tried all the ways to check it, then we have a fallback case, which is to synthesize a type, and then check that the type we synthesized is a subtype of the one we were expecting. And this right here is the only time we ever check for subtyping. And in a system that's not subtyping, but maybe where your compatibility of types is like alpha equivalence modulo computation, this is where you would be computing your normal forms, or it's where you'd be inserting your implicit arguments if you're implementing AGDA, things like that. And it's only here. And so our synthesis rule for type annotations, we get an annotation that E is a T, so we check that E is a T and return T. And then at the very bottom of check, which is what those vertical dots are representing, then we synthesize a type for our fallback, and then we check that it's an appropriate subtype, and then we're done. And okay, so now we've done that, and now it's time to go through all the syntax in the language and figure out what mode to run it in. So if we have the variable rule, where x can be known to be a T by looking it up in the context, well, that sounds awfully like synthesis. And as we've seen, it indeed works that way. And so the code for variables says that we look it up in the context and we return the type that we found, if indeed we found a type. For application, well, let's see. There's no T1 on the bottom of the line. And so if we want to follow our mandate of not inventing new information or not guessing, that means we're going to be needing to do our E1 in synthesis mode to discover what the type of the function is. And once we do that, we can then check that the argument has a suitable type, but we know the return type, so we can synthesize the type for function application. And our implementation, well, we match the result of synthesizing a type for the function, and we see that it is indeed a function type from T1 to T2. So we check that the argument's a T1, and then we return T2. For lambda, well, we've already seen what happens when we try to synthesize a type for lambda, so I'm just going to show you the answer immediately. We expect a type to be coming in from whatever context we're using the lambda in. And then if we have our lambda x body and we are checking that it is a function type, then we check the body and then we're done. And type annotations, well, we've seen how that rule works, but the implementation of it says that to synthesize a type in gamma for E annotated with T, we check that E is a T, and then we return T. And also remember, you may need to check that T is a valid type. And to turn around, then anyone else get total eclipse of the heart in the head when they look at this rule? In order to do that, well, it's at the bottom, so it's in checking mode, and then we synthesize the type for the expression, and that looks like this, as we've seen. So lists. We've already seen what happens if we want to synthesize a type for the empty list. It doesn't work out very well. So let's check these. So the empty list, we can check it against the type list T, and then we're done. And if we have E cons E's, where E's is just a meta variable standing for an expression as well, then we can check that it's a list T by first checking that E is a T, and then checking that E's has type list of T. And so the implementation for nil is that list of T, well, we see that the type coming in is list of T, and we're done. And for cons, we check that the head of the list is a T, and we check that the tail of the list is a list of T's, and then we're done. For recursion over lists, so the way to read this operator here is that rec list T of LBS. So L is the list we're doing recursion on. B is the base case to be returned when the list is empty. And S is the step to be applied to the head of a non-empty list, the tail of a non-empty list, and the result of recursion on the rest of the non-empty list to get our result type. So it's kind of like fold R with a couple more arguments, because I think this version is more convenient for a lot of purposes. Well, we've got our T right there, so we can synthesize the type. And note that we also have to synthesize the type for the list, because nowhere in that expression do we see the type of the entries in the list. And we need that in order to check the type of the step. So the target is what we call that sometimes, the thing that we are doing recursion on. That has to be synthesized, and the rest of the parts of this get checked. And so to synthesize a type for recursion on list of type T with target L and base B and step S, we synthesize a type for the target L. We see that the type is list of U, where U is some other type. We check that the base case has the appropriate return type, because if it's the empty list, this thing had better have the right type. And then we also check the type that we listed for the step, and then we're done. We return T. Natural numbers. 0 is a natural number, but 0 is also an int. So how are we going to express that? The way we can express that in this case is to say that 0 has any type that is at least as large as nat, is the way to read that rule. And then add1 of E has any type that is also at least as large as nat, assuming that the argument to add1, or the thing that we are embiggening, is that type as well. And so because T didn't appear in the bottom, we need to do it in checking mode. And so we want to check, if we want to check that 0 is a T, then we check that nat is a subtype of T. And if we want to check that add1 of E is a T, then we check that nat is a subtype of T, and then we check that E is a T. There's a convention here, which is that the premises of rules, when we're reading them as an algorithm, are read from left to right and top to bottom, the way that most European languages are read. So so that's why I'm doing the nat subtype check before I'm doing the recursive call. And for primitive recursion on natural numbers, well, we've seen how to do recursive operators, right? We synthesize a type for the thing we're recurring over, and then we check the type of the base and of the step that we're doing. And so the code implementation of this, we check that we synthesize the type for the nat, we ensure that the type we synthesized was nat, and then we check the base is our return type, and we check that the step is a function from the smaller nat to the result of recursion to create the new recursion result. Integers start getting kind of fun. So when we have this predecessor operator, well, we don't really know that, this rule is conservative, right? So according to this rule, the sub1 of 5 is not a nat. We don't get to conclude that sub1 of 5 is a nat. On the other hand, if you really wanted to talk about the predecessor of 5, you could have just written 4, so maybe no big loss. But in any case, we check that it is an int by checking that its argument is an int. So this is also in checking mode. And we recur down into the argument just as we did before. For recursion on ints, well, we've got a step to use for add1s and a step to use for sub1s. And these two steps are what allow us to recur down towards 0 on our ints. And so, but other than that, it looks just like the nat one, and so do all the modes and directions of everything. The target should have been int there, I apologize. The code is correct. Trust the code. So it says that, so we synthesize a type for n, and we see that it's an int, and then we check that b is a t. We check that our positive step is a function from ints to functions from t's to t's, and likewise for the negative step. So you may be thinking, all right, so you've just given me a bunch of rules, but how do I figure this out? I might want to make languages with things other than nats, ints, and lists and functions. Well, I've kind of categorized these parts that do checking and the parts that do synthesis and the parts that are sort of on their own into 3 categories here in the grammar of the language. So the first category are all the things that we did in checking mode. In other words, we have lambda, we have 0, we have add1, we have sub1, we have empty list, and we have list cons. So all of these are what are called introduction forms or introduction rules. And that is to say that they're the things that allow us to make something new of that type. So when you add a new type to your language, you say, like, what are its values going to be? What are the sort of the fundamental things that build it up? These are your introduction forms. And if you do these in checking mode, then you'll be safe. The others are the elimination forms. They are what allow us to use something of a particular type. So we use a function by applying it to an argument. We use a natural number by recurring over it. We use an integer by recurring over it. And we use a list by recurring over it. And then there's also variables, and then there's type annotations. And those aren't really introduction or elimination forms, and that's okay. We know how to use those. So we have this recipe, but sometimes we may want to be just a little bit flexible. So I'm reprising the rule that we had for recursion on lists. So the reason I like to put a type on my recursion operator saying what it's going to build is because that's how you have to do it when you implement dependently typed languages, and that's most of what I've implemented. So in those languages, the sort of the type argument there is explaining the relationship between the thing you're recurring on and the type you're building. Or in other words, it's explaining what predicate it is that you're proving as you do induction. And we shouldn't expect machines to invent that for us. That's a matter of human creativity. On the other hand, in a simply typed language like this, maybe it's a bit too bureaucratic. So what we can do instead is make a new version of recursion on list, and we can get away with this. So we say that we have to use it in a context where we have an expected type, so we're going to do it in checking mode, and then we don't have to annotate it with a type. And that's probably a design win here. You also have to be a little bit careful when you start messing around with these things, because it is a little bit easy to mess it up. So here are the rules for integers and natural numbers. And, well, 0, we can actually just synthesize the type nat for. And the reason why we might want to do this is because if somebody's loads up our programming language and they're sitting at their REPL and they type 0, it'd be kind of frustrating if the computer says, I'm sorry, I can't do that. You haven't told me what type you want. Because there is sort of a unique best type for 0 that's easy to find. So we might as well just find it for people. Add 1, on the other hand, is not so easy. Because if we want add 1 to work here, then we would need to, if we wanted to to synthesize the type t for add 1, then we'd have to know in advance what the type of the argument was. But if the type of the argument is something that we instead want to be checking, then we'd have to have a type annotation down inside of our successor constructor, perhaps. And that could get frustrating. So you probably actually, in a language with this particular configuration of subtyping, don't want to synthesize a type for add 1. And then for subtraction of 1, well, that one we can actually synthesize again, because that's always going to be an int. So we're okay. As long as we're checking the type of the argument, we're okay. So just a little bit of history, in case you are inspired by this and you want to go implement a bidirectional type checker and see some of the design space and what other people have done. The first published instance I know of a bidirectional type checker is in a paper by T.I. Concocts, which is called An Algorithm for Type Checking Dependent Types. It's published in SCP in 1996. And in this paper, there's actually not he doesn't make a big deal out of it being bidirectional, because this is like a thing people knew how to do when they're implementing programming languages. It's just not a thing that had been sort of written down in the academic record. It was like, oh, I'm writing a compiler and I'm going to do it this way. And then 2 years later, there's a paper in Toplas by Pierce and Turner called Local Type Inference. And this is the paper everyone cites who hasn't actually read it, saying, this is where bidirectional type checking was invented. And in fact, they make a really nice type inference algorithm, but they say oh, this is like a thing compiler hackers have been doing for a while, and we're going to use it in our theory, and because it actually works really well. And then they do good work on that. And so they're not claiming to have invented it. And then there's this great paper in ICFP of 2000 called Intersection Types and Computational Effects, which, I mean, those are two things that are pretty hard to put together, and you can do it with bidirectional type checking. If you go a year later, then you see the paper that describes an algorithm that eventually gave rise to the Scala type checker, called Colored Local Type Inference. If you're interested in dependent types, you might want to read Ulf Norell's PhD thesis, which uses a bidirectional approach to inserting like implicit arguments and collecting constraints on types. And then there's a really wonderful paper from ICFP 2013 that I highly recommend called Complete and Easy Bidirectional Type Checking for Higher Rank Polymorphism. And this paper tells you how to build a language that has higher rank polymorphism, but where most of the, where all the programs you could type in Haskell and Haskell would synthesize a type, this one will do it too. But you can also get your higher rank stuff, and it's way easier than most of the other approaches. So really a great one. And so just in summary, just so you remember things, bidirectional type checking is a technique in order that you can use to take a declarative type system that doesn't have an algorithm and make it syntax directed so that you'll have an algorithm to check those types eventually. It requires fairly limited annotations, in most realistic cases only at the top level of a function definition, and depending on how fancy you get, maybe not even there. It scales to a lot of advanced features, way beyond what an approach like Hindley-Miller can do, like subtyping, dependent types, higher rank polymorphism. And it gives you a really predictable place to throw your error, which gives you good source locations. If you want to learn more about it, then there's some lecture notes by Frank Fenning on bidirectional type checking that are very good, a tutorial by Joshua Dunfield. And then back when I was figuring these things out, I didn't know about those two tutorials, so I wrote one too as a PhD student. And so you can also read that. It's on my website. Thank you very much for coming and for your careful attention. Yeah.